Section: Introduction. In this section, we discuss modern information retrieval (IR) models, which typically match queries to passages using a single similarity score. This approach can make searching frustrating for users, as they often need to find specific keywords, apply various filters, and refine their searches to get the results they want. To address this, we introduce Promptriever, a retrieval model that can be guided by natural language prompts. For instance, if a user wants to find James Cameron movies released before 2022 that were not co-directed, instead of going through multiple searches, Promptriever can adapt its relevance criteria based on a simple instruction like, relevant documents are not co-directed and were created before 2022. Promptriever operates as a bi-encoder retriever, using a large language model, LM, like Llama 2.7b. Before training for IR, language models can easily adjust their outputs based on natural language prompts. However, after standard IR training, which usually focuses on optimizing a single similarity score, the ability to follow instructions is often lost. While some recent studies have incorporated instructions into training datasets, these are typically fixed templates applied to every query, rather than tailored instructions for each instance. In contrast, Promptriever is designed to retain the ability to follow specific instructions for each query. To achieve this, we created a synthetic dataset of 500,000 query passage pairs, each paired with unique instructions. The two main innovations in our training set are 1. Instructions that define relevance in diverse, free-form language, and 2. Instance-level, instruction negatives, where a query passage pair may seem relevant on its own, but a specific instruction reduces that relevance. For example, an instruction might ask for detailed information not found in a relevant passage. This design forces the model to adjust its understanding of relevance based on the instruction. Promptriever not only performs well in standard retrieval tasks but also follows instructions more effectively than previous models. It achieves state-of-the-art performance on instruction following retrieval tasks, showing significant improvements in robustness to query length and phrasing. Additionally, it demonstrates reliable performance improvements through zero-shot prompting, allowing for effective prompt engineering. We believe that with the right training data, modern bi-encoders can be guided by free-form natural language, similar to LMs. We hope this connection between the LM and IR communities will lead to further advancements in dense retrieval models. For data generation, we start with the MS Marco dataset, specifically the Tevatron August version, which includes hard negatives. This dataset contains around 491,000 queries, each with a positive passage and 30 hard negatives. We enhance this dataset by generating instructions and mining instruction negatives. In the instruction generation phase, we create specific instructions for each query. For example, for the query about volcano eruptions, we ask a language model to generate instructions that add requirements or exclude certain types of passages. We use Llama 3.70b instruct to produce these detailed instructions at scale. To ensure a variety of instructions, we ask Llama 3 to generate instructions of different lengths and styles, ranging from short sentences to longer paragraphs. The generated instructions can reflect different personas, negations, or general background information. Overall, LLAMA3 effectively meets our specifications for length and style, as detailed in our tables. Section Summary. In this section, we introduce Promptriever, a retrieval model that utilizes natural language prompts to dynamically adjust relevance criteria for search queries, enhancing user experience by eliminating the need for complex filtering. We detail our innovative training approach, which includes generating diverse, instance-level instructions and instruction negatives, allowing Promptriever to outperform existing models in instruction following retrieval tasks. Section: Maintaining original MS Marco positive relevance. In this section, we focus on maintaining the positive relevance of query, passage, pairs from MS Marco. We provide both the query and the positive passage to the language model when generating instructions, ensuring that the more specific instructions keep the passage relevant. To verify this, We use FOLLOWIR7B, a cross-encoder that can assess the relevance of query, instruction, passage, combinations. We found that about 15% of the generated instructions made the original positive passage irrelevant. In such cases, we replace the original passage with one generated in the next stage. Next, we introduce instruction negative mining. After generating the instructions, we can train models using the same data as RepLLAMA, but with queries enhanced by instructions. However, these instructed queries do not alter the relevance relations in the corpus, meaning models could ignore the instructions and still perform well. To address this, we create a complementary data augmentation called instruction negatives, where the passage is relevant to the query but becomes less relevant when the instruction is added. To minimize training loss, the model must learn to consider both the query and the instruction. Our initial attempts to find instruction negatives within the MS Marco collection were unsuccessful, as there weren't enough positive passages per query to identify nuanced instruction negatives. Therefore, we turned to generating passages using a language model. We used GPT-4 to create one passage that is both query positive and instruction positive, along with 3 passages that are query positive but instruction negative for each query-instruction pair. We generated more candidates than needed and filtered them afterward, as our tests showed that only about 2 out of 3 generated passages were correctly classified. We again employed FOLLOWIR7B for filtering by ensuring the generated instruction negatives were indeed instruction negative and that the instruction positive passages were relevant. For filtering validation, we had 4 human annotators assess whether a given query, instruction, generated passage, triplet was relevant. The average agreement among humans was 75%, while the agreement between humans and the model was 84%. This indicates that FOLLOWIR7B serves as a reliable filter. In our experimental settings, we aim to demonstrate the effectiveness of instruction training and information retrieval compared to standard training. We primarily compare our results to RepLLAMA, using their data and methodology for a fair comparison. For training, we use Promptriever on the RepLLAMA MS Marco data along with the new instruction data generated by Llama 3 and GPT-4. We maintain the same learning rate and hyperparameters as RepLLAMA for consistency. We include all valid instruction negatives in training and sample hard negatives from the RepLLAMA dataset, ensuring the same number of hard negatives per query. For evaluation, we assess our model on in-domain, MS Marco, out-of-domain, BEIR, and instruction following retrieval datasets, including Instruct-IR and Follow-IR. The instruction following datasets evaluate instructions on a per-query basis. We use various metrics, such as NDCG at 10 for BEIR and MRR for MS Marco Dev, along with specific metrics for instruction following datasets. We primarily compare our results with RepLLAMA for consistency, but we also present results from other models, including Minot 5, instructor models, and others. Section Summary. In this section, we focus on generating instructions that preserve the positive relevance of query, passage, pairs from MS Marco, using FOLLOWIR7B to filter out irrelevant instructions. We also introduce instruction negatives to enhance model training, ensuring that our approach is rigorously validated through human and model agreement, while comparing our results against RepLLAMA and other models across various evaluation datasets. Section: Results. In this section, we present our results. We find that Promptriever outperforms the original RepLLAMA in following instructions while still showing strong performance in standard retrieval tasks. For instruction following, we see from the table that Promptriever is the top-performing dense retriever, improving over RepLLAMA by 14.3 percentage points in PMRR and 3.1 in NDCG, MAP. We also include results from 3 cross-encoder models, which, as expected, perform better due to their higher computational power. However, Promptriever achieves similar results as a more efficient bi-encoder model. This indicates that our instruction data is very effective for dense retrievers, leading to notable improvements in instruction following and prompt robustness. In terms of standard retrieval, we evaluate Promptriever on two tasks, one within the same domain, MS Marco, and one outside of it, BEIR. The results show that Promptriever performs similarly to REP-LLAMA on in-domain tasks, while also excelling in instruction following. We also explore the use of prompts to enhance retrieval performance on out-of-domain data. We test whether specific prompts can reliably improve performance in Promptriever. For the BEIR dataset, we find that Promptriever's performance is comparable to REP-LLAMA, averaging 55.0 compared to REPYAMA's 54.9. We follow standard practices in the language model community for testing prompts, using a small validation set to select prompts. We create 10 generic prompts for use across different datasets. Our results show that using the best prompt significantly boosts Promptriever's average performance on BEIR, while prompts do not help REP-LLAMA or BM25 models. The selected prompt column indicates that there is little difference between the scores for the best prompt and those selected in a practical setting. In most cases, the best prompt chosen from the validation set leads to improved performance. We also analyze the sensitivity of all models to prompts. Promptriever shows much less variance in response to prompts compared to REP-LLAMA and BM25, suggesting it is more robust to input variations. Overall, we conclude that instruction training can benefit dense retrievers like Promptriever, especially when they are designed to be responsive to prompts. Additionally, we confirm that significant performance gains can be achieved by selecting effective prompts using a small evaluation set. Finally, we conduct an analysis to understand which aspects of the Promptriever training contribute most to its performance. We train several ablated models on a dataset that combines MS Marco and instruction data, and we present the results in a table, with REP-LLAMA as the baseline. Each row represents either a null hypothesis or a design choice that led to the final Promptriever models. Section Summary. In this section, we demonstrate that Promptriever significantly outperforms REP-LLAMA in instruction following and maintains strong standard retrieval performance, achieving notable improvements in metrics like PMRR and NDCG/MAP. We also find that using carefully selected prompts enhances Promptriever's performance on out-of-domain tasks, while showing that it is more robust to prompt variations compared to REP-LLAMA and BM25. Section Q1. Is it simply the length of the query instruction that enables Promptriever's performance gains? In this section, we address several questions regarding the performance of Promptriever. First, we clarify that the length of the query or instruction alone does not account for the performance improvements. We conducted experiments where we repeated the query to match the instruction length and used generic instructions. We found that while longer queries slightly improved standard retrieval performance, they had minimal impact on retrieval sensitivity. Specifically, the repeat query method showed a small increase in scores, and generic instructions provided a bit more improvement. Next, we explore whether the lexical distribution of instructions contributes to these gains. Our findings indicate that it does, but only partially. By training with real generated instructions while randomly swapping them for each query, we observed more significant score improvements, suggesting that the model learned the distribution but not how to apply it effectively. We also examined the impact of training with instructions. Our results show that training solely with instructions, without instruction negatives, led to a notable increase in retrieval sensitivity and a slight improvement in standard retrieval scores. Furthermore, we found that incorporating instruction negatives significantly enhances performance. This addition resulted in a considerable boost in retrieval sensitivity and a minor increase in standard retrieval scores, aligning with our expectations that instruction negatives provide valuable data for sensitivity but not necessarily for standard metrics. We then assessed whether additional training on the MS Marco dataset benefits our model beyond the curated Promptriever training set. Our final model, which combines both MS Marco and instruction data, demonstrated a significant improvement in retrieval sensitivity due to the increased amount of training data. In summary, each component of our final approach, training with instructions, instruction negatives, and MS Marco, adds independent value, and these improvements are not merely due to factors like query length or lexical features. Lastly, we consider whether this process is effective for other models. We initially used Llama 2 as the backbone for both RepLLaMA and Promptriever to ensure a fair comparison. Although we maintained the same training hyperparameters, we also tested different language model backbones to evaluate performance without adjustments. While further tuning could enhance results, our findings indicate that other backbones yield comparable performance, demonstrating the versatility of our method.